First, I'm going to, yeah. Today's speaker is Professor Zhang in University of Utah. He'll talk about structures of neural network effective theories. Please start.
Yeah, thank you so much.
Yeah.
Thanks a lot for inviting me to give this talk. So I'm gonna keep the video on if that's okay, but if the network, if the connection is not good, just let me know. I can turn off the video to see if that's better. Yeah, so I'll be telling you about a very interesting interplay between neural networks and field theories that I've been quite interested in recent years. And this talk in particular is based on a paper that we just put out in May with my former colleagues at UC Santa Barbara. So I guess whenever we find a correspondence between two seemingly different objects, there could be something that we can learn about each of them from the other direction. So it's kind of cool to see this. The plan for this talk is that I'll start with a high-level summary of this correspondence between neural networks and field theories. And then I will go into a bit more details on how to write down an effective field theory of deep neural networks. And I will specifically work out the EFT action for neural networks and at initialization before training. And then I'm going to introduce a diagrammatic approach to perform calculations in these neural network EFTs to make things simpler. And in particular, it makes the structures of these EFTs transparent. And from there, we can say something very interesting about the phenomenon of criticality in these systems. So let me start with a high-level summary and tell you about this connection. So let me start with something very basic just to make sure that everyone is on the same page. So what is a deep neural network? Basically, the goal here is that we want to learn a function y equals f of x from the training data set for supervised learning. And the underlying function could be something very simple, like here we're just fitting a curve, or it could be something more sophisticated, like we're trying to see, inputting an image of cats and dogs, we're trying to figure out whether the image describes a cat or a dog. And you can imagine this is a highly non-trivial function that you want the neural network to learn. So regardless, the idea is that we want to have an architecture that we put together with a bunch of neurons, and we perform some very simple set of operations on these neurons. But in the end, the system is flexible enough to approximate basically any function we wanted to learn. So an archetype of deep neural networks is called the multi-layer perceptron, basically fully connected feed-forward neural networks. So here, the basic operation is that starting from the input, which is a vector in some d-dimensional Euclidean space, we're going to first calculate the first layer neuron values or pre-activations, which I'm going to denote by phi, which is kind of suggestive of what I'm going to bring up next. To get the first layer neuron values, we're just performing a linear transformation on the inputs. And then after that, we apply a nonlinear activation function, which, for example, can be hyperbolic tangent. And after that, we pass on to the next layer, the second layer, by performing another linear transformation. And these coefficients, W and B, are called weights and biases, respectively. And these are the parameters that we want the network to learn. And so these are randomly selected at initialization and then updated by gradient descent to minimize a loss function, for example, a mean squared error loss. So the idea of connecting neural networks with field theories is that instead of looking at a single network, we consider an ensemble of networks. And they're randomly initialized. So we can ask about the probability distributions of the values of phi in this ensemble. And in particular, for each neuron, we associate with it a scalar field phi of x, the pre-activation value as a function of the input x. And the ensemble statistics would be described by an action, p is just equal to e to the minus s, just as we do in field theory. And the reason why this approach can be useful is that there is a very simple limit. In the limit where the width of the network, denoted by n here, namely the number of neurons per layer, when n goes to infinity, then the neural network, the ensemble of neural networks correspond to free theories. So this is in fact already quite well known back in the 90s in the machine learning community. I mean, in their language, these are called Gaussian processes. But in the field theory language, Gaussian processes are basically free field theories. So that means if we want to consider neural networks that are used in practice, which are not infinitely wide, but still wider than it is deep. So when n is much greater than L, where L is the number of layers, then these get mapped onto weakly interacting theories, for which we can perform calculations in perturbation theory. So all this machinery can be useful for a variety of things. And one of these things is to study information flow through the network. And there is actually an analogy with arXiv flows in field theory. So basically, the input is the UV, the output is the IR. And I guess for a long time, people have had this kind of intuition that what the network does when it's being trained is that I guess the first few layers would identify the low-level features in the data. So here, using a specific example of image recognition, so the low-level features would correspond to edges and dark spots in the images. And then the mid-level features will be learned by the intermediate layers, say ears, eyes, and nose in the picture. And then finally, all of these are put together so the network learn about high-level features like identify a person. So all of this can be made more quantitative in this arXiv flow picture. I'm going to talk a little bit about this in the context of networks identification, not quite the training part, but this is something that we can learn something useful about via this approach. So when thinking about information flow or arXiv flow in this context, immediately we realize that the challenge here is that generically we get exponential scaling. And the reason is since when going from one layer to the next layer, we're multiplying by a weight matrix. So we're multiplying together a bunch of matrices. That means generically things are going to exponentially explode or exponentially vanish. And on the arXiv side, this corresponds to flowing to a trivial fixed point. And this is bad. We want to avoid this because this will correspond to either numerical instability or loss of information. So actually, we can do better than this generic situation. We can fine-tune the system to some critical point. And add a criticality, we actually can have power law scaling instead of exponential scaling. And this corresponds to flowing to non-trivial fixed point.
Hey, Zhengkang, here's a question. Can you hear me?
Mm-hmm.
Yeah. What do you mean by exponential scaling in information flow?
Well, I guess I just mean like if you calculate correlators of the neurons and track them as a function of the depth, right? So you'll get e to the plus minus L, where L is the depth. If there's power law, it will be L to some power.
When you compute these correlators, what partition function you are using here? I mean, based on this network you just constructed.
So what is our question? What am I using?
Yeah, because I mean, if you say you're computing the correlators and you're putting all this stuff in a web, so I assume that you have some partition functions that are going on. You sum over some field configuration. What is that configuration?
Right.
What's the partition function?
Good. Yeah, I'm gonna show you how that is derived in a moment.
Okay, cool. Thanks.
Sure. Yeah, so I mean, all of this, I guess there are some wild dreams that we may have. Maybe a theory of deep learning, because for a long time, people have been saying it's like a black box in your network. I mean, garbage in, garbage out, basically. But I guess in recent years, there have been a lot of progress to try to open the black box to see what is going on in deep neural networks. Why are these machines learning so well? And people are taking different approaches from different perspectives. I guess many physicists from different subfields are looking into this as well. And I would like to particularly highlight this excellent book by Robert Serda and Hanning back in 2021. So our work is largely inspired by this work. They proposed an effective theory approach to understand deep learning. So I guess the other since we have a correspondence, the arrow goes in both directions. We can learn more about neural networks, and maybe we can also have a new angle to learn about field theories. And I guess in this direction, I would like to also highlight a series of works by Jim Halvorson and collaborators. I guess so. Their works share a kind of similar spirit that compared to what I'm going to talk about, especially their recent work, which came out not too long ago. Yeah, that was a high-level summary. So now I'm gonna get into more details about how we can write down an EFT for deep neural networks, and then specifically work out the form of this EFT at initialization. So just to remind ourselves, to initialize a deep neural network, we first set out the network. We need to specify the depth, L, the number of layers, and also the width, or the number of neurons at each layer. And we're going to take the hidden layer width to be much greater than 1. So these, the depth and the width are the architecture hyperparameters that specify the network architecture. And then we perform this set of operations, linear combination, and then nonlinear activation function to go from layer to layer, and these weights and biases are the network parameters, which are initially drawn from some distribution, often taken to be Gaussian. So here we're going to focus on the case where we initialize the parameters with mean zero Gaussians, and variances are given by CW and CB. These are called initialization hyperparameters because they determine how the parameters are initialized. So as I said in the introduction, instead of considering a single neural network, we're considering an ensemble of networks, and we're going to draw all these weights and biases from these Gaussian distributions. And now we can ask, what is the action for this ensemble? Namely, what is the probability distribution for the values of the neurons? So we can actually derive the field theory action as a phi, which I'm going to start showing you on the next slide. And just to be clear about the big picture, so here we want to calculate observables, which are neuron correlators. And we can do these calculations in the same way as we do in field theories, just in the path integral. And then we can study, for example, how they evolve from layer to layer. So this will map onto the arXiv flow that I was just talking about. So now let's start deriving the EFT action. And to do this, we're first going to write the full probability distribution for all the neurons from layer 1 to layer L. as a product of these factors. So the probability distribution for the first layer neurons times the conditional probability distribution of the second layer neurons, condition on the first layer, of course, and then a string of these conditional probabilities. So for each conditional probability distribution, we can calculate by just integrating over the probability distributions of the weights and the biases and a bunch of delta functions, because once we have the weights and biases, we know how to go from one layer to the next. So further writing down the forms of these probability distributions, these are Gaussians, and for this delta function can be written as an integral over this auxiliary variable lambda. So from here, we can basically complete the squares and then integrate out W and B, and finally integrate out lambda as well. And all these integrals can be performed analytically, and the result is given in this equation. And I guess very simply put, what is going on here is that when we write the expression for the conditional probability this way, we're basically, by integrating over the W and B, we're basically making a Fourier transform with lambda, the dual variable, and then by integrating out lambda in the end, we're basically Fourier transforming back. So here we're first Fourier transforming some Gaussians, so we get Gaussians, of course, and then Fourier transforming back, we again get something that looks like a Gaussian. So in the end result is in terms of these fields. So these depend on the Lth layer and L-1th layer fields. With respect to the Lth layer fields, this is a Gaussian, right? So, but this is not a free theory because this factor in between, which I call G, this is an operator that depends on the fields at the L-1th layer. So here I'm introducing a shorthand notation, sigma acting on the L-1th layer fields. I would just put these arguments in the subscript. So G is a sum over the neurons, and then each term is actually a function of phi L-1. So this is actually an interacting theory with interactions between the adjacent layer neurons. So in addition to this term on the exponential, we also get the functional determinant in front. So this means there are additional interactions encoded in this. And how do we deal with this? So looking at this a bit, we realize that what we have been doing is quite similar to Faddeev-Popov procedure for gauge fixing, right? So this delta function, it seems like it's just picking a gauge, and then I mean, just as in Faddeev-Popov, we're integrating over some Gaussians and get something that is a functional determinant. So here the way to deal with this is to draw some idea from that standard procedure. We're going to introduce some auxiliary anti-commuting fields, which we may call ghosts. So we just exponentiate this functional determinant. So basically, this is a EFT written for both the neurons and ghosts. So the crucial thing is that for both neurons and ghosts, at the Lth layer, they couple to the same operator. And this means if we can draw the following picture. So at each layer, we write down the neuron and ghost fields. So for the Lth layer neurons and ghosts, they both couple to the L-1th layer neurons. They couple actually in the same way, and the chain goes on like this. So this structure means that if we want to calculate the loop corrections from the neurons and ghosts at the Lth layer to the neurons at the previous layer, then they will always cancel. But this is just as expected, right? So because the network has directionality, so neurons in earlier layers can affect neurons in later layers, but not the other way around. So it's nice to see that in this field theory action, what's happening is a cancellation between neuron and ghost loops. And this also means that if we want to calculate the neuron correlators at the out layer, the correlators of these guys, then we can basically forget about what's going on at deeper layers because their contributions will always cancel, which also makes sense because what happens at one particular layer should not depend on what happens in later layers. So for the purpose of calculating the neuron correlators, actually ghosts will not enter. It will only be the interaction between these neurons and the previous layer neurons that matter.
I have a question.
Mm-hmm.
Here, do the X coordinates label different neurons on the same layer?
No, X is the input. So just as in the field theory, we're writing down a theory for phi of X, right? So
Yeah.
X is the input space, or space-time in field theory.
Oh, okay. So your phi. Oh, okay. So it's phi evolves along the layers, and you have one.
Right. Yeah.
Okay.
Right.
And also here, what's the meaning of a ghost? In this, I assume that's more like a scalar field theory. So what's a ghost here?
Sorry, what's our last? I couldn't get the
what's
last
a ghost? What's a ghost here? Because I assume that this is a scalar field theory with no gauge symmetries, right?
Yeah, there's no gauge symmetry. Yeah. So the analogy I was talking about with Fadipova procedure is really superficial. I actually didn't have to talk about it this way, I guess. It's just that, I mean, I think in some other subfields of physics, people would just say this is like supersymmetrization. They don't want to call this ghosts, but yeah, I mean, it's really a superficial analogy. Yeah, I guess from here we can see their role is just to ensure that we have this directionality in how the network works. It's like an auxiliary tool we can use.
I see. Thanks.
All right, so now that we have derived the action for the field theory, we want to do some calculations. We want to calculate the neuron correlators with this action, and this actually can be facilitated by a diagrammatic approach. So let's recall what I just showed you a few slides ago. The neuron part of the action involves a bilinear neuron scalar fields coupled to this operator G, which is a function of the previous layer neurons. So first of all, if we just temporarily imagine that these phi L-1, these previous layer neurons, were classical background fields, then we really have a free theory for phi L, for the L layer neurons, and we can do calculations very simply. Like the 2-point correlator would just be given by the inverse of this guy, which is just G, and then the 4-point correlator, we can just do weak contractions, right? There are 3 permutations, and you just get products of the 2-point correlators. So now, phi L-1, they are not classical backgrounds, but instead they are also part of the path integral. They're to be integrated over. But to take into account their statistical fluctuations in this ensemble, that simply amounts to taking expectation values on the expressions on the right-hand side of these equations. And we can represent these diagrammatically. So for this first line, we're just going to use double wavy lines, like graviton lines, to represent this operator G. And putting a blob means we're taking an expectation value. And here, similarly, we're just connecting 2 of these graviton lines to a blob, meaning taking an expectation value of the product of 2 G factors. And the external lines are connected according to which neuron indices are equal. So here, I1 should be equal to I2, so these are connected to each other. And of course, there are permutation diagrams that I didn't write down here. So effectively, I mean, we can repeat this exercise for higher point correlators, and we'll see a pattern. It's just that every time we can just use this very simple Feynman rule, writing the coupling between the two neuron fields at the L layer to this operator G, which is an operator of the L-1th layer neurons. And then we just want to make sure to attach these double wavy lines to blobs, so no external wavy lines, because we are going to always take expectation values of these operators. So we can do even better, because in the end, we'll be interested in connected correlators. So this means it's convenient to decompose this expression into a VEV part and a fluctuation part. So the VEV part is simply putting a blob here, taking expectation value, and then the fluctuation part, which we call delta, is just the product of two activation functions minus its expectation value. Okay, and in what follows, I'm going to use a single wavy line to denote a delta insertion. So this is just the fluctuating piece, and only this piece will contribute to connected correlators, because whenever we put a VEV here, then this part will just get disconnected. So I guess one thing we can immediately see is that each interaction vertex, which is this diagram, comes with a factor of 1 over n. So this means that if we consider the n going to infinity limit, the infinitely wide network limit, we have a free theory with no interactions. And for finitely wide networks, which are the most relevant in practice, we can treat them as weakly interacting theories and calculate the observables order by order in 1 over n. In the end, we'll be interested in the arXiv flows of connected correlators, namely how these connected correlators change as a function of the depth. Then we just calculate them order by order in 1 over n, and it will turn out, as we will soon see examples of, the 2k point connected correlator will scale as n to the 1 minus k. So for example, a 2-point correlator will be order 1, the 4-point correlator will be order 1 over n, and so on.
Hello. I have some naive question. In the beginning of your talk, you said this sigma is a nonlinear function like a hyperbolic tangent.
Yeah.
And then is it crucial to have a nonlinear function for sigma when you argue this, I mean, delta stuff or not?
Yeah, good. So what I'm doing here doesn't really depend on what function sigma is. So even if sigma is a linear function, it can do the same calculation, and it's actually even simpler. But the thing is, in practice, when we use a deep neural network, we always want to use a nonlinear activation function, because otherwise we're just performing a bunch of linear algebra, right, from input to output. Because sigma is only nonlinear operation. So if sigma is also linear, then the output is basically a linear transformation of the input, which means that the network can only learn linear functions, which is quite restrictive.
Okay, thank you.
Okay, so now I've introduced the basics for using Feynman diagrams to do calculations. Let's look at some examples. Just let's start from the simplest case, the 2-point correlator. Actually, I already showed how this is calculated. You just put a blob on this basic Feynman rule, and this is just going to be given by the expectation value of this G operator. So as I said, we're going to expand in powers of 1 over n. And as we can recall, this G operator is a sum over contributions from the different neurons in the previous layer, and each term is a function of a particular neuron in the L-1th layer. And at leading order, which corresponds to p equal to 0 term, so k0 at the nth layer. We want to calculate just the linear order result. Then recall that when n goes to infinity, we have a free theory. So this means the linear order result is just given by calculating this expectation value in the free theory. Free theory means in the previous layer, the propagator will be given by k0 of the previous layer, right? So writing this out, this basically means we calculate this expectation value, assuming that phi at the L-1th layer are Gaussian distributed with k0 being the propagator. So this is a recursion relation. Given k0 L-1, we can calculate k0 L. And in turn, we can think about this as an arXiv flow for k0, the k0 as a function of L. And the UV boundary condition is just given by the first layer result, which is simply given by the input. And then we can track the evolution to deeper layers. So I guess I'm not showing the final result for specific activation functions. This is completely general. So for what I'm going to talk about, I'll just leave the result in this form, which is like correlators calculated in the free theory. Of course, for any specific activation functions, say hyperbolic tangent, then you plug it in, and this is just a Gaussian integral. That you can, sorry, it's not a Gaussian integral, but this is a well-defined integral that you can calculate either analytically or numerically. And this kernel, this is also called kernel recursion in the machine learning literature. This is actually a well-known result. But it's good to see that we can reproduce this. But then moving on to the connected 4-point correlator, things become a little bit less trivial, I would say. So let's see how this works out. So we're going to introduce the notation before extract out a factor of 1 over n, and there are 3 terms related by permutations of the 4 input points. And let's just look at one of them because the others are identical. So this is the diagram we're going to draw. So basically using the basic Feynman rule, but since we focus on the connected correlator, we only need to keep the single wavy line, the delta p's in this diagram. So here, crucially, there are 2 possible contributions depending on the neuron indices J1 and J2 on both sides of this blob. So if these two, so these are the neuron indices for the previous layer neurons. So if these J1 and J2 are equal, then we can just use the free theory to calculate this blob. And that means we can immediately write down the result, which is a free theory correlator of the product of 2 deltas. Free theory meaning we calculate with propagator k0. But when J1 and J2 are not equal, then we cannot just use free theory propagators because free theory propagators are flavor preserving. So think of these neural indices as flavor indices, right? So if J1 is not equal to J2, then a neuron field with index J1 cannot propagate into a neuron field with label J2. So there has to be some interaction that changes this neuron index or flavor index. So the leading contribution would come from inserting a connected 4-point correlator at the previous layer. Okay, so because the 4-point connected correlator can change the neuron index. And the result is written in this expression. So let me explain these factors a little bit. So these 2 factors, the correlators between 1 factor of delta and 2 factors of phi, these come from these 2 blobs. These are pretty straightforward. Both of them are calculated in the free theory with propagator k0 at L-1. And of course, we also have a factor of the V4 at the previous layer. And then we have a symmetry factor of 1/4 because interchanging these two internal legs gives the same diagram, same for these two internal legs. So finally, these factors of K inverse, these are a little bit more subtle. So naively, since we have internal propagators, we would imagine that you want to insert factors of K, but actually these turn out to be K inverse because actually when we write down these blobs, these already include these propagators. And the same is true when we write down this connected 4-point correlator. This also includes the propagators that go into this blob. So in the end, we're double counting. So actually for each internal line, we should associate a factor of inverse propagator. Sorry, was there a question? I think I heard something, but hello?
No,
Am I
yeah,
still
no.
on? Okay, just confirming. Okay. Yeah, so this is how we get this expression. And we can further simplify this because calculating a correlator like this, we can do with contraction, right? Contracting these phi's with the phi's contained in this delta. So we cannot contract these two phi's with each other because then they will give us the value of delta, which is 0. So we always have to contract the phi's with the phi's in the delta. So that amounts to taking functional derivatives of these deltas. And making weak contractions also produces factors of propagators, which exactly cancel these inverse propagators. So everything works out nicely, and we have this very simple final result. So this result is the recursion relation or the arXiv flow for the connected 4-point correlator. Given V4 at the L-1 layer, we can calculate V4 at the Lth layer in this way. So this result is not new. It was first worked out by Yaida in 2019. It was also derived in the book that I mentioned by Robert, Yaida, and Heinling. I mean, all these calculations were a bit tedious when done in other ways, but the diagrams just really make things very straightforward to calculate. So I guess since we have this powerful tool based on Feynman diagrams, we can do a lot more calculations. We can progress to higher orders in a relatively easy way. But here, there are some tricks that we need to introduce, which I'm not going to have time to explain in detail. But I guess the idea is that we introduce what we call star blobs, which are like the regular blob minus diagrams where those phi's are contracted with each other. So we are requiring that each of these phi's must be contracted with one of these deltas. So in the end, it's always going to be functional derivatives on these deltas. So when using this star blob notation, we can very easily calculate the 2-point correlator beyond leading order. So I just showed how to calculate K1, K0, the first term in this expansion a few slides ago. And now if we want to calculate K1, it's just given by these two diagrams. Okay? And each of them has a very simple expression. We can even go to the 6-point, connected 6-point correlator. And even here, there are only 5 diagrams. Which is not too bad. And for one of them, it's very easy to write down the expression. Okay, now how about 8-point? So 8-point is actually not too bad, although the expressions do get a bit lengthy, so we're only presenting the degenerate input limit. But here, I mean, there are about 10 to 20 diagrams. We just enumerate the various possibilities of how these elementary Feynman vertices can be connected to each other. So this is a very fun calculation, and I guess this is actually the first time that this result has been calculated correctly in the literature. Yeah, so that was the diagrammatic approach, and I guess in the last part of this talk, I'm going to come back to the question of criticality, which I think is really interesting to see from the point of view of this diagrammatic EFT calculation, because it makes the structures of why networks can be tuned to criticality transparent. So yeah, first let's recall the notion of criticality. So generically, since we're multiplying matrices together, we get exponential behavior. But that's bad because we would either have numerical instability if things are exponentially exploding, or loss of information if things are exponentially vanishing. So we want to avoid exponential behavior. So to do this, we can fine tune the network hyperparameters to their critical values. So we actually get power law scaling. So how does this work in detail? So let's start by looking at the 2-point correlator, and let's do the following exercise. Let's say at the L-1th layer, we're going to perturb the 2-point correlators by this small amount, delta G. And we want to see how this gets propagated to the next layer. Okay, so what is delta GL in terms of delta GL minus 1? So in the diagrammatic approach, this can be calculated as follows. So I'm going to use a small blob with a delta to label a perturbation or a variation of this 2-point correlator. And it's just given by this diagram, right? So it's like we have this blob, and then one of these propagators inside the blob, we pull it out and we say, let's perturb this propagator of the L-1th layer. And then we can simply write down the expression of this diagram in terms of delta G L-1, which is this blob on the top. And it's going to be convolved with this function chi, which we'll call susceptibility, because it determines how the Lth layer perturbation depends on the L-1th layer perturbation. So this chi factor is just given by this part of the diagram that's in the box. Right? So it's basically two functional derivatives on this delta with some prefactor. So roughly speaking, we want to tune chi to be unity, because if it's greater than unity, we're gonna get exponential growth. So K star here is the arXiv fixed point. So basically the value of GL when L goes to infinity. So it's going to approach a fixed point in an exponential way. And this fixed point can also be either infinity or 0, or some fixed value, some finite value. But the point is that if we can tune the network to criticality, namely if we can tune this susceptibility to unity, where unity here means this symmetrized combination of delta functions, then actually this perturbation is preserved exactly. And as a result, we don't have exponential solution, but instead we have power law scaling. So the 2-point correlator will approach the fixed point in a power law manner with some critical exponent. This is what we want. And the way to achieve this is to fine-tune the hyperparameters. So recall, I said at the beginning that there are the architecture hyperparameters, the initialization hyperparameters. So here is the initialization hyperparameters we can tune. So here is a numerical example of what's happening here. So CW is the variance of the Gaussian distribution for the width at initialization. So CW superscript C is critical value. So this is what we want to set CW to, is here. If we look at the 2-point correlator, so these are based on some numerical simulations that we have run. So these are power law scaling. For this case, it's just it just stays constant, and here is a power law scaling, is a log-log plot. Whereas for CW, less than the critical value or greater than the critical value, we can see clearly the exponential behavior, which we don't want. So all I was talking about so far has to do with just 2-point correlators. So we might want to ask, what about higher point connected correlators? Because even if we tune the network such that the 2-point correlators scale in the power law manner, but if higher point connected correlators blow up, then that means we still have some kind of instability or huge fluctuations. And that would also be very bad for practical applications. So we want to ensure that all of them to have power law scaling. But naively, we might wonder how is this possible, because we have already chosen our hyperparameters. We have already fine-tuned these hyperparameters to make the 2-point function well behaved. And we have more constraints, but we don't have more hyperparameters to tune. But actually, the solution to this puzzle is that there is a common structure shared by all the higher point connected correlators, which actually means that the same fine-tuning will ensure that they also have power law scaling. And to see this, let's first look at the 4-point connected correlator. We already saw the calculation, a very similar calculation a few slides ago. But here, in this context, we're going to perform we're going to do a perturbation or a variation on the 4-point connected correlator of the L-1th layer and see how it propagates to the Lth layer. And the diagram that would contribute to this looks like this. So immediately we see that it's just like what we had before in the 2-point correlator case, and then just repeated on the other side, right? So basically it's 2 factors of this subdiagram, which evaluates to this function chi, the susceptibility. So the end result is that the variation of the 4-point connected correlator is just given by this combination of susceptibilities. And once we tune the susceptibilities to unity, the 4-point connected correlator will also be preserved from layer to layer. And of course, the same also goes for even higher point connected correlators. So here I'm writing the generic case, ... meaning there could be arbitrarily high points. So here it's always going to be the same structure, right? So just get more and more powers of this susceptibility factor. So in the end, we see that by fine-tuning the susceptibility according to the criticality condition, at the 2-point correlator level, we can actually achieve power law scaling for all the higher point connected correlators. So this is a really nice result that we can see from simply drawing the diagrams and seeing that they have the same structures. And of course, we can also easily verify this numerically and plot the 4-point connected correlator for various different input points as a function of the layer. And we can see at criticality, all of them will asymptote to a power law scaling. So that's basically all I wanted to talk about. Just to summarize, I think the interplay between neural networks and field theories is really interesting to study, and we have in particular introduced the diagrammatic approach to EFTs corresponding to neural networks. And one nice thing that we can see from this approach is that the structures of RG calculation explains why we can successfully tune deep neural networks to criticality. Yeah, I guess that's the end of the talk. Thank you for coming, and I can take more questions.
Thank you so much. Thank you for a nice talk. Do you have any question in audience and in Zoom?
I have a question. Yeah, thanks for the wonderful talk. I was wondering whether you have, because you talk about this criticality issue and RG flow, I was wondering whether you can, you could have a ODE for beta function with respect to L.
You're asking what is the beta function, right?
Yes.
So here, because I was presenting the RGE as I mean, it's not an ODE, it's like a finite difference equation, right? Because
Yes.
the layer index is
Yes.
discrete.
Yes, of course.
Yeah, so I don't know exactly what you're asking, but so here all the RG equations are written in terms of the connected correlators, like how so what is V4 at layer L in terms of V4 at layer L minus one, right?
Yeah.
So I mean, you can write down the continuous version of that. That will be an ODE, definitely. But I guess in this context, we can as well just solve these finite difference equations to get
Oh, and
the solution.
I see. And that is actually the graphs that you just showed us, right?
Yeah, that's right. Yeah, let me
I
go
see.
back to that. Yeah, these are V4 of L as a function of L. So this is a
see.
solution.
I see.
Yeah, but these are just numerical results. I mean, we can solve, we can obtain the analytical solution. Oh, well, obtaining the exact solution is a little bit more challenging, but at least we can obtain the critical exponents analytically. And here it's just, we just initialized the neural networks on the computer and calculated, well, we initialized an ensemble of networks and calculated the ensemble average and made this plot. So yeah, each point is just at this layer, what is the connected 4-point correlator, which we can calculate numerically.
I see. And another question might be, I mean, here, because you have a neural network already, and you have a numerical handle on that, can you do this non-perturbatively?
That would be really interesting. So I guess in the large width regime, since it maps onto a weakly coupled, weakly interacting theory, then we can do a lot of things perturbatively as the 1/n expansion. Of course, another question you can ask is if we're away from this regime, then we will have some non-perturbative phenomena, and how much of those might be interesting to understand, and how much of those can be quantified. That would be very interesting. I haven't thought too much about it.
I see. And do you have a vision of what you just get for this criticality, like its relation with conformal field theory?
Oh, can you be a little bit more specific?
Because here it seems that by tuning, if I understand correctly, by tuning chi, the susceptibility, you have this power law behavior of this copy constants or the endpoint correlators. It seems that this is sort of a signature of there being a conformal field theory there. So I'm not sure whether you have thought about that.
I haven't. Yeah, I
see.
haven't.
Okay. Okay, cool. Thanks.
So could you show this plot of V4 again? Yeah. So here, so on the in 3 plus of them, you have some dips.
Yeah, so yeah, this is just
Equals
because
3
we're
over 4, and with larger errors. So what is the behavior different?
yeah, so this is basically because we're plotting the absolute value of the 4-point connected correlator, and here is just change of sign across the
Change
zero.
the sign.
somewhere.
Okay.
Yeah.
Mm-hmm.
In the end, is only the asymptotic behavior that's interesting.
I see. And another question is this kind of a picture extendable to spin off or spin on, etc., higher spin?
Yeah, that would be yeah, that would be really nice. But yeah, I don't currently know a way to implement that. I mean, how to? I guess the question is, if we want to, can we build a neural network that would correspond to your I guess correspond to some higher representation of the well, yeah, of the space-time symmetry, just the input space. Yeah, that I don't know if anyone has talked about this. Yeah, I mean, most naturally, these are scalar field theories, but yeah, of course, it might be possible to add additional structures to it. That would be very interesting.
And maybe this is some stupid question, but you show that the n going to infinity is a free theory limit, and the large n limit corresponds to a weakly coupled theory, right?
Mhm.
So then, I mean, if you reduce the size of n and the n comparable to large L, for example, then do you think your theory can mimic the strongly interacting scalar theory or not?
I guess that's definitely possible. I guess I mean, I haven't thought too much about it, but yeah, it would be interesting to see if in that case there are still some things we can calculate on the, I mean, controllably calculate. That would be very interesting.
I see. Wow, that's very interesting talk.
Yeah, thank you.
Thank you.
Okay. Any other question in audience and Zoom?
Maybe just one more.
Okay.
But that is probably just a wondering. Can you do fermions with neural network?
Yeah, I think that's what as Professor Ko just asked about.
Yeah.
Yeah.
Yeah. I was okay.
Yeah. So
Yeah, I have a follow-up question about the fermion. Just
Mhm.
naive question. Then you told me now you don't have any comments about the high spin field, right? By the way, do you have any plan to extend your work to cover the high spin field?
yeah, I think that's a very interesting and important direction. I don't currently have concrete ideas for how we might proceed. I mean, there are, I guess, various other directions that might be interesting to look into as well. I feel like this is I mean, this is a kind of an emerging field, like I guess both from the point of view of understanding machine learning theory from some physics methods, and from the point of view of like simulating field theories using some machine learning techniques. So I guess a lot is going on, and yeah, so I mean, these specific directions I don't really have very good ideas for at the moment, but yeah, it would be nice if someone look into those.
Yeah, I think it just as long as the how should the including the high spin fields such as spin 1/2 and 1 field is very crucial in order to make optimize this your work, because in practical application we have a lot of half spin field and vector version fields, right? So
Yeah.
maybe I think your final goal is to optimize your program to make many people use your program, isn't it?
Well, I guess there are many aspects. I mean, I guess even for scalar field theories, there are still interesting questions we can ask. Are there ways to like sample field configurations more efficiently than what people are currently doing on lattice, right? So I mean, even for scalar field theories, you can ask these kind of questions. But I agree,
Yes.
the more interesting applications will be if we can apply the same techniques to fermions and gauge fields. mean, that's basically marching toward solving QCD, but I mean, that's maybe a more long-term goal. Like right now, I feel like we have just started. Like because also, I mean, on the machine learning side, it's also like we're building some harmonic oscillator models, right? If you're asking me how does ChatGPT work? Can I understand ChatGPT using this framework? I guess we're pretty far from there, but we have a good starting point.
I see, I see. I think your work is very interesting personally to me. Yeah.
Thanks.
Yeah, it's very prominent. I think. Anyway, other question? If not, let's thanks to the speaker again.
Thank you. Thank you very much.
Thanks, everyone.
Thank you so much, and thank you for giving a talk, even though there is a evening.
No problem. Yes, this is a great time. Quick way to end the day, I guess.
Okay, I see. Maybe a few days later, our administrator will contact you, as I told you in email. Yeah, for getting your server information.
Okay.
And could you also send your talk file to the seminar organizers?
Yeah, sure.
Please. Yeah, please. Yeah.
Okay. Thank you very much again, and have a nice evening.
Have a
Yeah,
nice
thank you.
evening.
Yeah, have a good day, everyone.
Okay.
Thank you. Bye.